Welcome to Newline99. This episode is about TI-99 assembly language. The TI-99 4A comes with the basic programming language built in, but there are programming languages that give the user more ability to control the environment. Of all the programming languages, assembly language is the closest one to the machine level because it's a symbolic code that represents what happens on the machine level. The TMS-9900 is the processor in the TI-99 4A. Everything that the TMS-9900 processor and the rest of the hardware attached to it can do, assembly language is capable of directing. For the most part, BASIC is a platform-neutral environment. After you finish writing a BASIC program, you run it. The BASIC interpreter takes over, reading it in one line at a time, following the sequence of commands, and constantly acting as an interface to the processor, until there are no more commands in the program to run. Assembly language, on the other hand, is a language made specifically to address the hardware in specific ways. After you finish writing an assembly language program, you assemble it, which converts all of the symbolic representations into something the processor itself knows as executable operations. And when you run it, the result can be a very fast, very feature-rich program that does not require an interpreter and is not subject to the limitations of BASIC. There are a few different assemblers on the TI, but we will be covering the TI editor assembler. The editor assembler comes with a cartridge that you load at system startup, but the cartridge doesn't contain all of the software required. There are also diskettes that store some of the editor assembler code. There is also a large manual that comes with the editor assembler that is both helpful and frustrating. Looking for specific information in it can be a mixed bag, and sometimes the documentation makes assumptions that you already know some vital piece of the architecture, sometimes even skipping important information entirely. It is for that reason that it's good to reach out to the online community. In working with assembly language, especially if it's your very first time using it on any platform, you'll find yourself relying a little bit on those who came before you, people who can help point you the right way in this very unique language on this very unique platform. And whether you're new or not, a TI-99 emulator on a modern system can be a valuable asset in your assembly programming. Some TI emulators, such as Classic 99, provide you with a memory map, disassembly, register display, the ability to make breakpoints, the ability to step through the processor operations to help you understand why certain things are happening. The first important part of assembly programming is learning not to rely on how BASIC would best implement an operation, and replace it with how the processor would see the operation. Let's take an example of printing a letter X in the middle of the screen. The basic way to think about this is a call to HCHAR, indicate row 12, column 16, character 88. The assembly way to think about this is to take the byte value of 88 and copy it to the exact video display processor address we want, which is 367. We would accomplish this by placing 367 in register 0, 88 in register 1, swap the bytes of register 1 so that the 88 comes first, and run a library routine VDP single byte write. And that's it. The assembly equates to 15 machine code operations. And you're probably thinking to yourself, one basic line versus 15 machine code operations? How much savings could there possibly be to use assembly over BASIC? You would think that until you find out that interpreting this one TI BASIC line of code equates to 7,853 machine code operations, adding up to 1/10 of a second wasted in the interpretation of this line. The processor performs all of its operations using registers. First, there is a program counter, or PC. It keeps track of where the current operation is located. There is the workspace pointer, or WP, which holds a memory address of the start of the current workspace, which is where all of the values of the general purpose registers reside. The general purpose registers are used to hold the inputs and outputs of computations. The TMS-9900 has a whopping 16 of them, named R0 through R15. Status registers are used to store the states of the last computations, mainly for comparisons. Think of them as switches. They are bits, either on or off, keeping whether the previous operation resulted in a condition such as greater than, equal, carry, overflow, or odd parity. You need a place to store your operations and data while it's not currently being worked on, and so you need access to memory. Memory, of course, is a large array of space that can contain all code and data that you plan to use. The operations in assembly are referred to by symbols. You may also define your own symbols to make your code more human readable. A symbol that you create for readability is called a label. It can refer to a starting place to run code, a starting position of text or numeric values, or memory addresses where data is. Labels are typed at the very beginning of a line of assembly. In assembly, you tell the processor what to do by writing a series of operations the processor knows, identified by mnemonics, and it performs those actions against the input-output parameters called operands. Depending on the operation you use, the operand can refer to a value in a register, an indirect memory address in a register, a symbolic address, or an indexed address. You will find different ways to access information are useful in different circumstances. Be sure to put comments in your assembly code to make it easier to follow later on. A line starting with an asterisk will let you type comments in your program. Let's consider a practical use for an assembly program. I wrote a basic program to test joysticks to make sure all the buttons and axes are working. One where I update all button states to this screen every time I go through the loop, and another where I only display the ones that have changed since the last time through the loop. Both ran extremely slowly. Unfortunately, in BASIC, if you are testing the horizontal and vertical axes and buttons of both controllers every time through a loop, it can take a whole second to go through a single iteration. Assembly language would certainly speed this up. To start, we would have to get a few things out of the way. In order to run the assembly program, we will need to link to the assembly program from outside. And the way we do this is to use the def keyword to identify code that will be used to start running it. Like in the example before with displaying X on the screen, we'll be using the built-in reference VDP single byte write, but we'll also be using two other built-in references, VDP multi-byte write, which is VMBW, and keyboard scan or KScan, which will be able to check the joysticks for their current states. When the program starts up, we want it to display a title at the top. Like in the basic version, we created some special graphics to display the joystick positions and buttons. And we'll want to do the same in the assembly version. Starting from character 0, we'll plan to dump 11 character definitions into VDP all at once. 88 bytes. We'll define some addresses that we'll use to check joystick states. We'll need to change the keyboard scan mode to 1 for joystick 1, and 2 for joystick 2. We'll define the addresses where the joystick button, X-axis, and Y-axis states are stored. We will need to show the state of each button on the screen somewhere, and we'll hold those screen positions as an array of values in joy.pos. So we'll be able to display each joystick position by going through a simple loop. After we scan both joysticks, we'll capture all the values we receive in JState. Again, to make it easy to sweep through the list in our loop. We'll define where in JState we'll store each joystick component's state, and what the expected value is for that state. Up, down of joystick 1 will be in byte 0, left to right in byte 1, the button in byte 2. Joystick 2 up, down in byte 4, left, right in byte 5, button in byte 6. We start by displaying the title message at the top of the screen. Byte 5 in VDP memory sounds like a good place to start. Point to the text for the message and put its length in R2. We do the multi-byte write, and that's the end of that. Let's set our new character definitions with another multi-byte write. The characters in VDP start at hex 0800. Point to the characters we made above with the length we used above. Multi-byte write, and done. Now we can start checking the joysticks. This will be the beginning of our main loop. We momentarily turn on our interrupts, allowing the keyboard and joystick controllers to interact with the processor. Set keyboard scan to joystick 1 and run the keyboard scan. We copy our joystick and button findings into our little 8-byte JState buffer. Do the same thing for joystick 2. Now we've copied everything we need from the joystick controller. We'll prepare an inner loop to display all those states on the screen. Register R4 will point to the array with the locations on the screen to put the pictures of the joystick symbols. R10 will be our counter, starting from 1. Character 0 is blank, so we're skipping over it. R2 is 6, marking the end of the loop, after we've checked all 5 states, up, down, left, right, and button. We'll use register R5 to hold the offset for the joystick 1 information, R6 for the joystick 2 information, R7 for the expected value if the button or axis is pressed, for comparison. We compare joystick 1 to the expected states and expect to display a character on the screen for that joystick direction. But if that joystick state is currently on, we'll add 5 to it so that it'll display the filled-in joystick position to indicate that it's currently being pressed. If it is currently not being pressed, we jump over that part. Then we display it with a single byte write. We do the same thing to the values for joystick 2. Then we display them on the right side of the screen. After one pass is done, we increment our counter increment our screen position array by 2, compare if we've reached the end of the loop, and do that until we've displayed all joystick states. And we want the program to just keep doing that forever. We finish up with end, and we're done. Save the program to disk, jchasm/s. That's just a name that I picked. We'll assemble it and see if we have any issues with it. We need to load the assembler from diskette, so we need to do a little disk switching. And now we load and run the program to make sure it works as expected. Now on the TI-99 4A, we need to make sure that we press the caps lock key to undo it so that the joystick up directions will work. The program displays the title, shows all the joystick controls in a non-active state. Now if we move the joysticks and press the buttons, we should find it appears to display their states very quickly, a lot better than the basic program did. So it looks like it was a success. That's all we have for this episode. Hope to catch you again next time from Newline99.